right. Time to talk about what I'm sure will be everybody's favorite part of this chapter, dealing with the several different units of solution concentration and converting between those different units, which can be a little bit tricky, so we'll have to do some examples and figure out how that works. But there are several units of concentration. The one most important in chemistry is probably molarity, used pretty much anytime you have a prepared solution, right, that's in a bottle, it will say what the molarity of that solution is. That's very common. And molarity is so common because it's easy to deal with. It is moles of solute per liters of solution, and we use that very often. You know, preparing a solution of a certain molarity is not difficult. You just calculate out how many grams you need, you know, based on the, you know, it's a pretty simple calculation. You do volume to moles to grams, pretty much. And then you dissolve it and you use a volumetric flask and you bring the volume of the liquid up to a total solution volume. So whenever it's molarity, we've never measured out how much solvent. We never talk about add this much water. We only talk about add enough water to make this much solution. Okay? So that's the important part of this whole thing, the whole mixture. So, for instance, a 1 molar solution would just mean we got 1 mole of NaCl dissolved to make 1 liter of solution. Okay. Would we make a 1 molar solution if I took a mole of sodium chloride and dissolved it in a liter of water? No. Yeah, because then the solution volume would be greater than 1 liter. Whenever you dissolve something, when you dissolve a solid, usually the volume goes up. If you're dissolving a liquid, the volume could go up or it could go down based on whether the new intermolecular forces are stronger or weaker than before. If you're mixing two things that have stronger attraction than they did alone, the volume will actually contract a little bit. But I think the one thing that you can remember here is that volumes do not add up right. If you have 500 milliliters of water and 500 milliliters of ethanol, those will not add up to 1 liter of solution. Okay? In that case, what is that? In that case, it is greater because because the water-hydrogen bonds are the strongest there, and you have ethanols in between them, so it's a little weaker. Acids and bases, things like that, where you're making ionic products, it'll contract a little more because you have stronger attractions. You have ion dipole forces. Okay? So to get around that, all we do is make a solution based on total solution volume, and then we always know what we're talking about. Okay? That's what we do with molarity, but there's a problem with that if you are doing an experiment that involves a change in temperature. Because as you change temperature, the density of the solution will change slightly, but it'll definitely change. So without adding or removing any solute or water or anything, you will change the molarity just by changing the temperature. Okay? The molecules are moving faster, so it spreads out a little bit. Now you have a lower molarity because you have the same moles dissolved in a greater solution volume. So that's a problem when we're doing calculations that involve a temperature change, right? Because which molarity do you use? Do you use it before or after or something like that? So to get around that, there is a variation called molality, and you have to be careful with your m's. Molality is a lowercase m. Molarity is a capital M. So be very careful with that. And lowercase m does not mean mass. Be careful with that. It's molality. So spot the difference here. Still moles of solute on the top of the fraction, but look at the bottom of the fraction. Kilograms solvent. So two things different. Okay? We're not dealing with volume of solvent or solution anymore. We're not dealing with volume at all in molality because volume changes with temperature. Okay? We're dealing with the mass. Mass does not change with temperature. Masses are additive. Obviously, if you have 4 grams of this and 4 grams of that, you got 8 grams total. Okay? But look at the other difference. It's not kilogram of solution, it's kilogram solvent. So I'm going to sort of circle both of those things. Okay? So mass is constant with temperature, and notice now we're talking about solvent, not solution. Okay? So and molarity is the property, and we say molar with a value. Molality is the property, and molal, lowercase m, molal, NaCl, would contain 1 mole of sodium chloride, again, but then it was 1 mole dissolved to make a liter of solution up here. This would be 1 mole of sodium chloride with what? Yep, 1 kilogram of H2O. Okay. Now, if the solution is very, very dilute, okay, if we have a tiny, tiny concentration, molarity and molality will be very similar, right? Because if we have only a little bit of solute, that won't change the volume much, right? And if it's water, at least, a kilogram of water is 1 liter, okay? So, molality, let's do similar to for dilute AQ solutions. Okay? So, sort of a way to check your work. If you've got a fairly dilute solution and you're converting between those or something like that, they shouldn't be that different. Okay? Now, obviously, if you've got half of the mass as solute and half of the mass as solvent or something like that, the molality and molarity will be drastically different. Okay? But at low concentrations, they're similar to each other, but we use this in the case where temperature is changing, or in cases where we're talking about adding things and combining things and so on like that. Okay? So we'll get examples of that later on. Parts by mass and volume is used fairly commonly in, especially in very, very low concentrations. So, you could have molarities down to 10 to the negative 6 molar or something like that. Right? You could use tiny scientific numbers. But when you're talking about really small concentrations, what you'll usually see is parts per million or parts per billion. When they were cleaning up after that chemical spill in West Virginia, they said that now the concentration is finally below 1 part per million or something like that. But when you're talking about really small concentrations like that, they use that sometimes. Anyway, okay. So parts by mass looks like mass of solute divided by mass solution. Okay? Anytime we're doing one of these parts by, it's always the total on the bottom. Okay? So whatever it is we're talking about, divided by the total mixture. Okay? If it's by mass, it's like that. If it's by volume, it's like that. Sometimes, very rarely, there's a combination one used where you have a certain mass of the solute for a certain volume of solution. That's kind of antiquated, so we don't use that a lot anymore. But so if all you did was do that, you would get some fraction out of 1. Okay? You'd be going 0 to 1, kind of like we did with mole fraction before. But typically with parts by mass or volume, we multiply it by some kind of multiplication factor to give us our actual unit. So we've talked about percent a lot before. A percent is just this, because we multiply by 100. That makes it out of 100, and we use the unit, the percent sign. Okay? If instead of doing times 100, we do times a million, that's parts per million. Okay? Times a billion, that's parts per billion. Okay? So that's all that is. There's nothing fancy about that. It's just a different multiplier, essentially, that gives your value a different scaling factor. So one really easy way of interpreting anything that's parts by, whether it's percent or parts by million, parts per billion, is to set up a relationship where that number is an amount of solute, and then sort of the multiplication factor is how much solution you're talking about. Okay? It works by just sort of taking care of that multiplication factor. So 14% by mass means 14 grams of solute per 100 grams of solution. We just use the unit to tell us what we're talking out of, essentially. Okay? How much out of that 14 is. Okay? 25% by volume means 25 milliliters of solute per what? 100 milliliters. What? Solvent? Yeah. Whether it's by mass or by volume, it's always out of a total solution. Okay? Really, the only place we use solvent is molality. Okay? So this is solution. Okay? So, atmospheric CO2 is listed in parts per million, but sometimes it's parts per million mass, and sometimes it's parts per million volume. You have to be careful because those values are a little bit different. So, right now, the latest value I found, atmospheric CO2 around 582 parts per million by mass. The by volume is actually a little more commonly used sometimes, but that's okay. So that's that value. If the mass of the Earth's atmosphere is 5.14 times 10 to the 18 kilograms, that's a weird number to know, but that's the mass of the atmosphere just based on what the atmosphere is made out of. How many kilograms of CO2 are in the atmosphere? Let me show you a way of setting this up so the units cancel. But essentially, this is just kind of like a percent problem. But what I would do, understand that I've got 582 parts per million, which means I'll have, oops, where did we go here? 582 units of mass of CO2 per 1 million units of mass of atmosphere. Right, total. So those units can be whatever you like. It would be nice if we did it in kilograms, because that's what we're being asked about. So this works out pretty nicely. If we do 5.14 times 10 to the 18 kilograms of atmosphere, we can set up something over here that makes that original unit cancel, right? What do you suppose I could put right there? There it is.
582 milligrams.
If we said 582 kilograms of CO2, then that would be per how many kilograms of atmosphere? Million, 10 to the 6. See how that works? That's because we're talking parts per million. So could be any mass unit as long as it's the same. Okay? That could be grams or kilograms or milligrams or whatever, as long as it's the same mass unit. That tells you the ratio, 582 of CO2 per million of total. I got 2.99 times 10 to the 15 Shows you it's kind of interesting how powers of 10 work, right? 582 out of 1,000,000 seems like a fairly smallish concentration. It's less than it's about a half out of 1,000. It's 0.05% or something like that. Okay, but when you're doing it on huge powers of 10, 5.14 10 to the 18 of atmosphere total, about 3 times 10 to the 15 kilograms of that is CO2. So gives you an idea of how much CO2 is hanging around out there. The interesting thing that I thought right here is that it's been shown that just 200 years ago, CO2 was 450 parts per million by mass. So if you put that in terms of actual kilograms or even tons of CO2, you could calculate how many more tons of CO2 we have in our atmosphere that have been put there just over the last 200 years. How do we know what the ppm of CO2 was in 1800? Anybody know where that comes from? They didn't have CO2 probes back in 1800. In fact, we've only been able to measure CO2 in the atmosphere for 20 or 30 years or so. Yeah, they use ice cores for the range of 50 to 500 years or so, something like that, or even longer. They use ice cores because especially in Antarctica, because it doesn't evaporate too much. Any ice that's put down stays there for pretty much forever and just gets compacted with the ice that's below it. And any CO2 that was in the atmosphere is going to have a proportional amount dissolved in the water that made up that ice. That's Henry's law, right? So they can calculate for as deep as they can go in the ice, they can calculate what the atmospheric CO2 was just based on that sample. So the key thing you need to get here, ppm just means 582 out of 1,000,000. 582 of what we're talking about out of 1,000,000 of the total mixture that it's contained within, right? If we were doing parts per billion, we'd just do 10 to the 9 there. If we were doing percent, we could have 100 in there, although 582% doesn't make sense, but if it was 0.582% or something like that, it would just be that out of 100. Okay. Does that make sense? Okay. We dealt with mole fraction a little bit last semester when we were talking about mixtures of gases. Mole fraction is just simply moles of solute divided by total moles of solution. So it's kind of a mole by mole comparison of your solution's makeup. So this script X is a Greek chi. So just draw kind of like a cursive X or something like that, so it doesn't look like something else. Okay? Just based on that formula there, if we have several different things that are in a solution, all of those mole fractions should add up to what? Look how that works. Yeah. If we got nothing, okay, that's a mole fraction of 0, right? Because if we had 0 solute in a solution, that's a mole fraction of 0. If it was a pure substance, we would have 1 mole of solute, which is also 1 mole of solution or whatever, right? We would have, so mole fraction can only be between 0 and 1. Okay. So the sum of all the mole fractions in a solution is going to add up to 1. So you can use that if you know the mole fractions of everything except the solvent or something like that. You could subtract from 1, or you could use that to check your work or something like that. What does it mean if a mole fraction of something is 0.5? Yeah, it is half of the total moles. And what if that solution is made up of just 2 things? What if we have a mixture of 2 things, and if mole fraction is 0.5 for one of those? What does that mean? Yeah, the other one's mole fraction is also 0.5. So essentially it means the mole solvent if it's a two-component mixture. Okay. So if we have a mixture of A and B, a 0.5 mole fraction means we have equal amounts of those two things. Okay? So let's take, I'll leave that there for you to see it. Let's take the example of 8.2 grams of sodium chloride dissolved in 16.7 grams of water. This time we specified the mass of water that we used. Okay? So pretty much 8.2 grams of sodium chloride, and then we weighed out 16.7 grams of water. Okay? Or we used a corrected density to get to that. So let's calculate percent H2O by mass. Percent NaCl wouldn't be tough, right? You'd just do, well, here, let's just talk about percent H2O by mass. We're so used to thinking of, if sodium chloride is dissolved in water, we're used to thinking of what is the concentration of NaCl, but we don't have to. We can talk about the concentration of water, too. When I do percent of something by mass, we'll want to have the grams of that substance up on top. So in this case, it's going to be grams of water on top, right? Just what we got right there, 16.7. Okay? But what needs to be on the bottom of a fraction when it's a percent or parts by mass? The total solution, right? So 8.2 plus okay. So just dividing those two would give you a fraction out of 1, essentially. What do I have to do to make it a percent? Times 100. And you can put the percent unit there if you want. This is percent by mass. Just look at those numbers. Is it going to be greater than 50% or less than 50%? Yeah, it's going to be greater than 50%. I mean, if they were both 8.2 grams, you'd have 50%, right? This is going to be closer. This is going to be closer to 70%, I think, if I'm looking at it right. Anybody else want to borrow a calculator? I'm going to have other ones for you to do. Who needs one? I mean, this one's not too bad, but I'm going to give you kind of a doozy here in a minute. So what'd you get? That's you, well, 3 sig figs? Well, I don't know, because we had to add 8.2 and 16.7 down on the bottom, and we go by decimal places for that. So, but that's over 20, right? What's 8.2 plus 16.7? Somebody just type that in quick. Yeah. So that is 3 sig figs down there. If this was just 8 and 2 or something, 2.2 or something like that, we'd be 2 sig figs worth. But so you have to be a little careful when you're adding to make sure you're not dealing with sig figs like you shouldn't be. But so yeah, it is the 3 sig figs. That's not so bad. Okay. What does that script X mean? Mole fraction of NaCl is going to mean moles of NaCl over what? Total. So mole NaCl plus mole H2O. How do I get moles of NaCl out of 8.2 grams? So if you're going grams, how do you get moles? You guys know how to do that. Molar mass, 58.44. Yep. Because that's how many grams there are per 1 mole. You're going to have to do the same thing for the water. Divide that by 18.016. Okay. If you're writing any of these intermediate values down, keep some extra sig figs so you don't have a rounding error. We've only got 2 sig figs from our 8.2. So what'd you get for moles NaCl up here?
0.1403.
Yep. Okay. And then moles of water. I can't read mine at all, so you're going to have to tell me that.
0.92695.
Yeah, that looks going to. Looks like it could be right. So I'm just going to write that over here. 0.1403 divided by the sum. But all the way down to 2 sig figs, I'm sure, because of the that's going to be there. So, anybody get a mole fraction? Point 13. Okay. Would a mole fraction of 13 make sense? No, mole fraction has to be between 0 and 1, otherwise you're not doing a mole fraction. Since we already got the mole fraction of NaCl, and it's a 2-component mixture, what's the fastest way to get the mole fraction of water? Yeah. Point 87. You could also, you should get the same answer if you took 0.92695 over the total moles. Should still get 0.87. It's a place where you're anywhere unsure of your number crunching. You can do it both ways to make sure you get the same answer. That'll save you from computation issues sometimes. Of course, it won't help you if your moles are wrong. But okay. So everybody okay on mole fractions? Does that make sense? Moles of one thing divided by moles added up. That's always what mole fraction is. Okay? And everybody gets the difference between mole fraction NaCl, mole fraction H2O. It's just what you have on top. Okay? What does this mean? Molality. Molality is moles on top divided by, because it's molality of NaCl, so I want moles of NaCl on top divided by what? Kilograms of water. So moles of NaCl, we had that was 0.1403. How many kilograms of water do we have? 0.16?
0.016.
Careful. 3,000, right? 1,000 grams per kilogram. So move the decimal point 3 times 0.0167 kilograms. Looking at those numbers, it's going to be less than 10, more than 5. What'd you get?
8.4.
8.4? Yeah. Now is this, how many sig figs is this? Yeah, 2 again, because of the 8.2 grams. So 8.4. Feel free to write moles per kilogram, if you like, or 8.4, what? Lowercase m.
How do you say that again?
Molal. Let me write that out. Molal. That's how you pronounce that. This is a molality. Just like instead of saying molarity, we replace that R with an L. So instead of saying 8.4 molar, we say 8.4 molal. Wonder where those names came from. It's a weird way to say it, but their names are more similar than their calculations. Okay, questions? How come I don't have a molarity? How come I'm not asking you to do a molarity calculation on this page? I didn't give you liters. Well, it's not 16.7 milliliters? No. What would I have to know, actually? What would you have to be given? Either total solution volume, or if you had the density of the solution, you could figure it out. We'll probably have to do that on the next page. Lydia.
Okay, what are the units for the 0.13 and the 0.87?
Oh, where? Oh, no units.
We don't have
Mole fraction has no units because we have moles here. Moles plus moles are still moles. So mole fraction has no units. It is a these percents and the parts per million and so on, those would also have no units, except we multiply them by a multiplication factor that has a unit. Okay? So the only reason percent has that unit is because that's what this 100 is. So, but yeah, mole fraction, let's write that up here. Mole fraction, no unit. Okay? Yeah, mole fraction is dimensionless. pH has no unit because it comes from a logarithm. Other things that are ratios like that can tend to have no units. So, okay. Questions? Those? Okay. Ready? At least clear what we're talking about there? Okay. This one is going to suck a little bit, if I'm being honest. Because, and the thing is, this is a calculation that I've had to do more times than I can count. Because, look at it. When we buy concentrated sulfuric acid, the most concentrated sulfuric acid is, what it says on the bottle, it says it's 94% H2SO4, H2O. Okay? So it's a little bit deceptive to say in H2O, because what's there more of? H2SO4 or H2O? Yeah, it's 94% H2SO4, which means it's 6% H2O. I don't know if that's going to come in handy later. Sometimes it does, but when it's a two-component mixture, the two things that are in it, their percents add up to 100%. Okay? So they give you that on the bottle. That's how concentrated sulfuric acid is sold. They give you the density, 1.83 grams per milliliter. But we very often need the molarity of that. Good lab managers usually have a cheat sheet of molarities of common concentrated acids, but this is how we calculate it. So when you're given a mass percentage, assume you have 100 grams of solution. Right? That's just taking that percent and turning it into out of 100. So if that's the case, how much H2SO4 is in there? 94 grams. And how much H2O is in there? Okay. On a different question, not this one, but on a different question, where might this grams of H2O come in handy? What concentration unit has a mass of water? Molality. Okay, so keep that in mind. You'll probably have to do one of those at some point. This would have a really weird molality because we're only dividing by a small part of the solution as opposed to the total. Okay? So I asked you for molarity. The molarity of this solution would be what over what? What would be on the top of the molarity fraction? Moles of, and what's the solute here? Yeah. Technically, before I might have said the solvent is what you have more of, but that's not necessarily the case here. The solute is whatever is the substance quoted after the concentration value, pretty much, right? So we would need moles of H2SO4. I think we can do that. But what would we divide by? Well, for molarity. Liters solution. Okay. Okay. So we're going to still take that. We're going to take that 100 gram assumption. That's usually the missing piece when students get stuck on a problem like this and you don't have anywhere to go. If you're ever given a percent or given a ppm or ppb or something like that, assume your solution is the actual amount that unit would suggest. So if we have a percent solution, assume we have 100 grams of that solution and go off of that, for instance, to calculate moles. So why don't you see if you can calculate mole? Should I give you the molar mass?
You have it.
Yeah, I think I got it here. Molar mass, 98.086. Because it would say that on the label, too. Okay? But you all know how to do molar mass. I assume on an exam you'd probably have to add up the molar mass from the periodic table. Okay? So that's getting that part. $94. Here, I'm going to use a different color here. .086. So, what'd you get for moles?
19583
Okay.
moles of sulfuric acid.
Okay.
0.3330 moles of H2O. Or, well, sorry, not.
Yeah, if we were doing mole fraction, yeah, if I wanted mole fraction, you would convert those grams into moles. That's fine, but that's not what we're doing. Okay. Not so bad. All right, what are we going to do about this? Not only just liters, but liters of solution. I'm open to suggestions. Start with 100 grams. I like that. Okay. Start with 100 grams of solution. I probably wouldn't multiply it by the density. I would use the density to cancel its unit, right? 1.83 grams per milliliter. Right? Yep. Convert to liters. 1,000 milliliters per liter. That's going to give us liters of solution. That's exactly what we want. That's pretty neat. Hmm. 0. So the way I see it, if it was just water, we'd have 0.1 liters. We'd have 100 milliliters. This is more dense than water, so we're going to have less than 100 milliliters. We're going to have, yeah. It's not going to be as low as half because it's not 2, but it's going to be almost half less, so 0.054. Okay. That has, from here, that has 3 sig figs. From here, that has 2 sig figs. And then we've got what we need. Oops, 6. So, molarity?
Is it 17.64 or 65?
Sort of.
It's 2 sig figs.
Yep.
Sig figs, so it would be 18.
Yep. What would we need if we wanted better than 2 sig figs there? We would need a better percent. And very often, so how many digits you get on the percent depends on what grade of a reagent you're getting. So, and they're not always good about sig figs, but they'll give you a tolerance. They'll give you a plus or minus. So the lowest, the technical grade will be plus or minus 1%, which translates to 18 molar, pretty much. The technical or so lab grade is the lowest, then technical, then quantitative, then chromatographic. There are 5 or 6 different grades of it you can get it for. So there's nothing stopping you, however, from taking a lower grade like that with a bigger plus or minus and actually titrating it and figuring out accurately what its concentration is. But like I said, a decent lab manager will have a cheat sheet that lists molarities of common concentrated acids, and concentrated sulfuric acid is 18 molar. So one of the higher molarities of the acids. So concentrated sulfuric acid is so nasty because it's 18 molar, and as we'll also see, it has 2 acidic hydrogens. So if you're doing molarity of actual hydrogens, it's going to be twice that. In your mastering chemistry, you'll probably have to do a conversion that goes one way or another between molarity and molality. You can use these same sort of ideas, but if that's ever the case, if you're ever given a concentration and converting to another concentration, take your given concentration, write out what its this per this is, and assume you have a solution that has that amount. Assume the bottom of your fraction is how much solution we actually are given. That gives you a place to do the calculation, at least. Okay? So if you're given a 4 molar solution, you would start with 4 moles of the solute per 1 liter of the solution. Okay? You would probably have to get grams, and you'd probably have to use the density to figure out total grams, and then you could subtract to figure out how many grams of that are just the solvent. So, but doing those, unless you got other information, that usually requires density. Okay. It's going to be grams of solution, liters of solution. That's what the density calculation is going to be. So that's how we got our liters of solution for the bottom of the molarity in here. If we were ever solving for molality, we would need grams of solution in order to subtract grams of solute to get grams of solvent. So, all right. So, like I said, your mastering chemistry will give you some practice on that, but I didn't want to put it up in the notes because it's kind of ridiculous, but the textbook has a gigantic figure that has every concentration unit and arrows going between all these different units that says all the ways that you get from one thing to another. It's worth us putting it up in the notes like that because you look at it and want to hurt yourself, but it's useful. It's useful if you are stuck on a problem because it'll usually give you the hint that you need. You know, if there's a missing piece that you need to go from one to another or something like that. Okay. So, questions about that one at least? Anybody? Feel good? Okay. So,